De loin parce que j'ai rien entre eux. Ce que je dois faire, je dois tout repasser.
Arbeit eintragen. Dass die Leute zurück mit Kaffee kommen.
Ça m'occupera le bureau. Peut-être que je l'aurai pas d'ailleurs.
Ladies and gentlemen, we will start again the presentations.
Si tu n'aimes pas.
Just a few minutes for people to go to the desk. Bonjour, c'est à toi.
Non, c'est... Ah, on commence? Je croyais que c'était l'autre présentation avant.
De Alex?
Oui. I thought it was yours first.
Ladies and gentlemen, please come back to the room. We will slowly start the next session.
On va se barrer au club alors.
Ladies and gentlemen, it's time now to get back to your seat. We will start the last session for this morning. We are back on the Airworthiness session, and we are welcoming Louis-David Germain from Transport Canada and Brian Kellogg from Aerometals for a presentation dealing with an update on SAE S12 Committee on AMC for IBF power available and distortion.
Merci Clément. Good morning, everybody. So this morning will be a presentation on an update presentation on the S12 committee on the IBF. We will start the presentation with a quick introduction of the inlet barrier filter for those that are not familiar with the concept, given by Brian Kellogg from Aerometals. Then we will discuss the S12 committee, how it's built, and I will touch quickly on the document itself. And I expect a few questions, so the slides will be brief, but we'll have a chance to answer questions after. So Brian?
Thank you. Good morning, everyone. As Louis David mentioned, we're going to cover just a couple of basic topics for barrier filters. Most of you probably already know about this content, but if not, here you go. A couple of pictures here. The inlet on the left is an unfiltered engine, and on the right-hand side, you can see the same engine is outfitted with a barrier filter. In general, the barrier filters are made up of a pleated and oil-impregnated design. Typically, we'll see 99% or better filtration efficiency. There are some products out that are using a dry media that doesn't require oil. Basic concept, the air that used to go in the engine is forced through the media. The media collects the sand, dirt, and debris, and as that continues, a pressure drop builds over the filter or creates inlet depression. From there, these systems have a differential pressure switch or a transducer, and that measures the pressure drop or inlet depression, pressure drop across the filter. Some designs will provide a real-time filter blockage that shows, gives pilots a situational awareness. They may include individual engines. Other designs will have a switch that's set to illuminate at a preset threshold. If the system has one, a bypass door can be opened, and that provides power recovery to the engine, allows unfiltered air to go directly through and bypass the filter media. The dirty filters can then be re-oiled or washed and cleaned and re-oiled, and typically that would restore most all of the clean filter engine performance. In general, we find that most operators keep a standby filter oiled and ready to go to decrease the downtime, which is often approximately 24 hours to clean, dry, and re-oil an oil-type media. A couple of pictures of these in action. This particular aircraft was operating down in Chile, Argentina area, and they're off airport, very sandy, dirty runways, landing conditions. And typically that would cause erosion, sometimes FOD. This is an actual part removed from the aircraft. They had to overhaul their engine around 800 hours. Through the overhaul process, they found about 32 grams of dust in their hollow shaft. They later installed a filter, and the same part made their TBO at 1,500 hours, and it came out clean without any indication of buildup. So what's the effect? When a filter's installed, there's an initial loss of power. Depending on the inlet, the engine, the filter design, that can range anywhere from 1%, perhaps up to 15%. As mentioned before, as the contaminants are collected and the pressure increases, the power available will decrease. And then once the filter is clean, the power is restored again to near clean levels. And this cycle of building up debris and cleaning and building up debris and cleaning is repeated typically until TBO is reached. So in addition to power, there's a potential effect on distortion. Addition of a filter could improve or could worsen distortion depending on the aircraft, the filter design, and therefore needs to be verified. A side note, typically we found that filters will reduce the pulsing distortion that's caused by rotor blades, and in installations where an engine may be sensitive to this, we'll see improvement of power and performance when a filter is installed. So with that, I'll hand this back to Louis David, and he'll update on the status of the S12 committee.
So the SAE S12 committee includes about 100 members. Obviously, not all of these members are voting members, and not all of these members are participating in the IBF discussions. The main role of the S12 is to maintain documents, and right now we have 32 documents. 3 of them are work in progress. So here are some statistics. We're following the footsteps of Thomas Edison and Henry Ford. So a little bit more than a year ago, the FAA requested that the SAE committee create an ARP to provide means to substantiate that the IBF doesn't exceed distortion limits, mainly focused at 901, and also define means to determine and verify that the power available as affected by IBF is determined correctly as per 41C. So as you may expect, if there is a difference in power available, it will affect other regulations. The committee will also look at those. So the draft ARP Actually, the numbers already been chosen. It's going to be 6912. And this is the title. So substantiation of power available in inlet distortion compliance for rotorcraft IBF installations. In March, 20 members of the S12 committee formed 2 subcommittees. Each of those subcommittees include representatives from the power plant, engine, airframe, and flight test disciplines. And the 2 subcommittees are power available and the distortion. Some people are on both of those subcommittees. So the scope of the ARP is to identify and define methods of compliance to power available and inlet distortion requirements for IBF installation. So you will see that paragraph in the main document. It brings me to the next slide, which is the meat of the document. So the document will discuss the important definitions for IBF. So it will look at the IBF as a system. Right now, a lot of the STCs and even the installation during TC include the IBF, look only at the filter itself. It's not recognized that the IBF is actually a system, including subsystems. Not just the filter, but also the sensors, bypass door if there's one, and the human-machine interface. The document will discuss the types of contaminants, including icing, although icing will be dealt with another SCE committee. So this document doesn't help you with certification for icing. It helps you for determination of power available and distortion. And then we will clarify the definition of what is a clogged, blocked, or contaminated filter. Those words have been used in the past interchangeably, but we'll try to clean it up and provide some recommendations. So the hot topics, I will read them to you. If you have questions, feel free to ask, but I will likely not respond to them. Involvement of the engine manufacturers during design and testing. This is mostly aimed at the distortion subject. Right now, a lot of the STC applicants feel that they are left on their own when it comes time to certify the IBF filters, where bigger OEMs have more access to the engine OEMs. Same thing for the airframe manufacturers. Some of those STC applicants have difficulties dealing with the airframe OEMs. So we will tackle those topics, see what the recommendations from the industry are. We'll try to provide acceptable performance penalty and power assurance check procedures, flight test demonstration methods, and we will treat the use of bypass air as a mitigation. So that's something that was tasked specifically from the FAA. Bypass is not required all the time. It is a mitigation to a problem. So we will try to tackle that more as a 1309 style assessment. So as all of us do so well, I have a unrealistically over-aggressive schedule. So we estimate that the finalized draft will be by the end of this year or early next year, and submission to the FAA of a document by this summer. So that completes the presentation, and I'll let Alex talk about the next topic, but I will be open for questions after. Thank you very much.
1, 2. Okay, there we go. So, I'm not gonna bother you for a long time. I know it's coming to the lunchtime, but it's a presentation on the fly-by-wire, and what we've been doing recently on a large aircraft that came out of validation in Europe and certification in the United States. So I'm going to give you a small briefing about, the fly-by-wire. It's it's an old topic. It's been like for years out there. So I've got it very basically, where basically we have a history of 30 plus years. So we need to talk about where we are and where do we go with this thing. How do we get there? And what we've learned so far from the exercise. So I'd like to ask you for an apology because I don't have pretty pictures inside the presentation. I've got just boring text. But the text has a good meaning. So as you all know, we had more than 30 years of experience on fly-by-wire control laws, either in the United States at NASA, Ames, or at the Bell 205 at the NRC, at the National Research Council of Canada, at the Flight Research Lab. And there was a huge school of thought that has been developed since the 60s and 70s on fly-by-wire, fixed wing. But later on, it transmitted into the helicopter. So all of this, as the time passed, appeared at the top level with the aeronautical design standard, 33, C, D, E, F, and so on, which was actually used as essentially a harmonization tool of a language between the flight test and the designers. It did give some design targets for engineers to understand what the flight test pilots and engineers were talking about. But traditionally let's put it like that, in the West school of thought, it has been the main tool for feedback from the flight test to the designers. Now, of course, as most of you know, most test pilots have been trained on those aircraft. As far as I know, there were, for decades, 2 or 3 aircraft in the Western world being able to simulate a variety of other aircraft, other flight conditions, and so on. So essentially, it's like you give the people the feeling of something else with variable stability. So yes, we have a lot of test pilots trained for that. A lot of people know about it. A lot of people can explain what they want and how they feel it, but there is no harmonized flight requirement at the top level, at least for the civil world. So, yes, we do have the fixed wing experience, which is great. We also learned from the introduction of fly-by-wire fixed wing aircraft that they were very difficult to manage at the beginning. They had to do a lot of retraining. The people had to do a lot of retraining, and there was a huge impact the way that an aircraft was flown. Now, imagine the helicopter now, which is being used in a much more complex operational scenario than a fixed wing. With all the apologies to my fixed wing colleagues, we're not flying only straight level or straight, and everything else is a byproduct of banking or whatever. We have 6 degrees of freedom, really 6. Basically, when we're flying straight level, we don't have a big issue with designing control laws. That's not a big deal. But when it comes to hands-on flight, aggressive maneuvering, ground tasks, then the whole situation changes. So, on top of that, the fixed wing experience had given us the confidence that once we take a fixed-wing aircraft, put it in the aerodynamic tunnel, identify all those fancy aerodynamics, design the control laws for the blown-up extrapolated case, it'll work. So there are not many changes that you would actually expect to take place when you start flight testing the aircraft, when you have the prototype essentially out there. But what happens in the rotorcraft, and every large manufacturer knows this, is that we have so many unknown dynamics that they're still posing risk for development. Just have a look at the prototype of every company that has come out from the aerodynamic design, and have a look at it later on once it's certified. You see all different geometries, different concepts, and this in the fixed wing is very difficult to imagine. So we cannot enjoy the usual compensating factors of the fixed wing projects. Like, we can't be sure that we will design a flight control system for 1, 2, okay. So we can't really design so easily something in the laboratory or on the ground, expecting that it's going to work outright from first flight, which is what our fixed-wing colleagues have very high expectations about it. So on top of that, as I mentioned earlier on, we essentially need the control laws to provide very simple control modes. I'm sorry about the terminology, moding or whatever. It doesn't sound very good in English, but still, it's reality that we're not using the aircraft like the fixed wing does. So, and on top of that, we don't really have the time to learn it. So it has to be very simple, but it has to take into account many, many different cases. So most of all is something that we shouldn't forget here. Everything else that I've spoken so far has to be really exercised within the financial constraints of the civil world. If you imagine a fly-by-wire military aircraft, rotorcraft, that has had like 5, 10, maybe 15 years of development experience and investments, I'm not so sure that this is something that it's easy to do, it's easy to achieve from the financial perspective within the civil world. Things are tighter, deadlines, deliveries, so that the effectiveness of the designers has to be a lot better. And of course, as we expect, we will see a dramatic change in the training requirements. I think our colleagues in the other group were talking about a future generation of rotorcraft, generation 6 or 5, I don't remember how they've been calling it, where essentially they're fly-by-wire rotorcraft. So, where do we go? Starting from Bell 525, a wonderful aircraft, which is the first civil application for a rotary wing application within EASA and the FAA. The FAA, Transport Canada, and EASA have really tried to cooperate and harmonize all the requirements and understandings that we had about the subject. And we have to take into account here, it is the first helicopter of such kind. So every time that you try to do something for first time, you're bound to make failures. You're bound to do something good, something bad. You have to come back and correct it. And on top of that, as I mentioned later on, is that the experience of each of the authorities is very similar. They've had the similar training, similar understanding, and so on, but not identical. And that's extremely important when you put flight test people and subjective opinions into the loop. So, but this is where we go. This is how this is where we were and where we go. And on top of that, we in order to enjoy the benefits of the technology and protect from the drawbacks of it, we must make heavy use of simulators for certification. And I will speak a little bit more about it later on. So, Basically, we need to arrive to a very good and representative simulator configuration in order to be able to take credit for it. And I'll give you some hints about how we think that this can be done later on. And all this is to minimize risks. Risk for development, risks for flight testing, risks for certification. So, and as I explained in my previous slide, is like we will have a significant difference in pilot understanding about what is the damn thing doing now. Is it, it does everything automatically. We're not in the loop to control it. We're not thinking about all those mechanical things that they taught us how to think about. So, the FAA came up with a substantial number of rules that helped this situation. We cooperated with them, and thanks to this cooperation, as validating authorities reviewed all of these and came up with 3 basic special conditions, which I would like to speak to you about today, about 3 topics that essentially carry the root, the meat of the fly-by-wire. By no means we can cover the subject here within a 20-30 minute presentation, but at least I can give you a flavor of it. So the first one is to control margin awareness. The first one is about envelope protection. And the third one has to do with flight crew awareness and modes of operation. Of course, apart from the special conditions as usual, we're doing something new. We have to crystallize our interpretations about interaction, systems, structure. So we have some additional project-specific interpretative material on a variety of topics like control secret integrity, compliance demonstration, and also I will speak about the simulator credit, which I mentioned earlier on, how this can be done. So let's go a little bit on case A, control margin awareness. Essentially, this is being, the root of that is because we do not feel fundamentally the limits of how we feel in mechanical helicopters or in limited authority systems, where a part of your actuator authority is being controlled by the flight control system and another part by mechanical links or via the trims. So we don't know where the classical stops, please note the quotes, are. So we cannot really know when we operate close to the limits. So only after actually we hit a limit, assuming that we didn't have some protection with it, on it, then we'll see the effects, and that's not gonna be nice, especially if you're high altitude hover close to the mountains. So we need to put forward compensating factors for the complete flight envelope. And here I want to make a distinction. We're not talking about just the HV envelope, high velocity. We're talking about envelope in all sorts of motions of the 6 degrees of freedom aircraft. We are talking about rotational velocities. We're talking about structural limits. It's not necessarily the classical thing that you see in a flight manual on an HV. So the control margin awareness is logical, may combine tactile, visual, and oral alerting. We don't want to limit to a tactile, like feedback, or we don't want to limit it to visual or to oral. Every particular case will have its own solution, depending on the stabilization system, depending on the effectiveness of the alerting and so on. So this is subject to assessment by the flight test crews. And of course, when we're talking about control margin awareness, we're not talking about necessarily each axis that we see or we fly. The limit, we have aircraft that you're limited on one axis and basically you don't know about it and you have to act on the other. So we're talking about the controllability limits, not each axis. So every aircraft manufacturer knows precisely what is limiting their aircraft in each particular phase of flight. And of course, very important that whatever awareness method of the margins we implement, we must reduce the nuisance. The last thing you want to see is something beeping inside your aircraft when you're hoisting someone in difficult conditions. So, a few words about the flight envelope protection. It's clear that we're looking into protecting the aircraft from the structural, aerodynamic, or operational limits. It's obvious that you're not controlling the aircraft anymore mechanically. The computer controls it. So the designers in the computer have to make sure that the aircraft is protected by all of these items. At the same time, the control laws can change dramatically when approaching or exceeding limits. And people that have designed previously fly-by-wire systems, be it the military, Black Hawk, NH-90, whatever, and S-92, they know very well that you have to do something about it inside the code, inside the flight control system, in order to avoid hitting limits. And you have to be compatible with structural limits of the aircraft. You have to be compatible with the safe and controllable maneuvering conditions, and here we're also taking to subpart B into account. Of course, blade stall, rotor speed, engine transmission limits, and so on. I'm not going to start going on about it, because it's endless discussion. So, most important also has to be like, we are talking about protection also in case of failure cases. So you lost an actuator, you lost some authority, which is not extremely improbable. So the aircraft must be capable of continuing to safe flight and landing. And of course, all of this has to be appropriately tailored for a standard pilot's skill or strength, as we used to say. This is not an easy task to achieve. So, the third part, flight control in all attitudes. Very important, the control responses have to be appropriate in all attitudes, and they must not disturb the crew to recover. So that means unusual attitudes, that means possibly extreme flight conditions. So the designers have to adapt their control laws so that the pilot does not fight the control law in order to control the aircraft. It has to be straight to his brain that in an emergency situation, what he needs to do very quickly to recover. So traditional flight control systems downgrade or disconnect automatic VHS. And this is very important because sometimes you can imagine you're flying in a perfect aircraft, fully controlled, fully functional, you've got nothing to do, you're reading a newspaper or whatever else, and suddenly failures come up. So you increase your workload rapidly in order to start compensating for those. No, we don't want that. We want so that the pilot intervention has to be gradual, so that he gets into the loop, he expects the bad things to happen, he expects what is coming to him. So whether that is as usual attitudes or whether that it's a very quick, rapid rotational velocity beyond normal operations. So if, for example, you get a very strong gust or you fly under a rotor cloud without realizing, you have to be able to react and very quickly. So in any case, the flight control system must continue to operate, and the design of the flight control laws, including any automatic protection functions, should not hinder the aircraft recovery. And this statement relates to the first bullet point, but it relates mostly to the automatic protection functions, because we do not assume that the pilot will always be able to recover. Some things might happen automatically, some things may happen manually. And of course, the flight displays must continue to provide support to recovery action. It doesn't matter if you say that my control law limits my bank angle to 5 degrees, 10 degrees, 15, whatever that is, and therefore I don't need to display anything more. No. You are able to go to unusual latitudes. You have to be able to give the pilot the visual cueing that he needs to recover manually without being disturbed by the flight control system. So, how do we get there? Simulator credit. How do we do this? How do we test all of this? In a simulator. How do we do that? We have an aircraft we don't know. We don't know its basic performance, based on which we have to model something on the ground which is equally unknown. So we need to, from the authority perspective, to accept as a risk minimizing feature a simulator performance which is very close to the real aircraft, and both of them are acceptable for certification. You can imagine the task. It's like you have one equation with two unknowns. You change something here, the equation is not solvable. So, but we're not going to reinvent the wheel. People have done it. People have done this in the fixed wing, and we can borrow some experience from their side. The only difference being that our steps will be a little bit smaller. By saying this, what I mean is that we need to develop the simulator very accurately with a very good configuration, as if it was the aircraft itself, practically. And every time that we go to flight test something, we must upgrade the simulator. We shouldn't have big gaps between them. We shouldn't proceed with the flight testing too far away when the simulator is too back, because maybe we didn't have money or we didn't have enough time to do it. So we have to really see it as a success part of our flight testing. Of course, it's needless to say that we need to rehearse all the flight testing to have people to maintain the configuration of the simulator. And then, of course, we go to, the top part, I think it's obvious to everybody. The bottom part is what essentially we have thought of asking about the representativity, excuse my language, representativeness, or whatever you want to call it. So basically, we need to have a simulator very close to something we don't know. So how do we do it? What's going to be the deviation of the simulator performance when compared to a real aircraft? Actually, we don't need to think too much about it, because our colleagues from Flight Standards have already had a solution for training. So if you go and look at the CSF STD, you will see a very, very long list of requirements: how much torque, how much velocities, how much you are allowed to deviate from, in order to be good for training. So it means if you're good for training, it means you're good enough, it means it's controllable, it means it's not dangerous to fly, so we don't have any negative training, basically, and we certify simulators for those things. So there's no reason why we can't use that knowledge on our side to say, yes, it is controllable, yes, we have a test pilot on board that is going to test it anyway, yes, we have to maintain essentially a simulator close to that level of how much our colleagues are doing on the flight standards. And again, don't be scared about it. We don't need to develop a second aircraft, because developing an aircraft is by itself a very long and expensive exercise, but developing a simulator is as bad as an aircraft. So we're talking about limited all these representations and demonstrations for those flight maneuvers that are intended to be demonstrated on the simulator. You don't need to demonstrate flying straight level flight on a simulator, but you do need, when you need to go down to duplex, triplex failure or whatever, and to stay without any control, you don't want to kill your test crew, basically. So when we're going to talk about simulator credit, we're going to talk about only for those maneuvers that have been defined by industry to be demonstrated there, not everything, like the flight standards do very often for the whole, the whole flying part. So, for each case, what we want essentially that is demonstrated is that the flight dynamics representation has to be argued, has to be demonstrated. And The good thing is that if we follow the ideas of the flight standard group, essentially we will end up with a structure that is going to be very similar to what is requested in the CSF-STD rule. So essentially, it will be a help to industry to start working in this way, because later on, when they have to build a simulator to go and train their customer pilots, and they need to approve the simulator, by the way, in order to do this job, then they have to start working in the same way, without having to reproduce documentation, reproduce knowledge, and all this kind of stuff. So for our part, for our certification part, we plan to use the simulators for basic understanding of how initially appropriate the control law is, for thorough evaluation of the failure cases, of course, as I mentioned earlier on, due to the integration and the complexity of the failure cases. So at the end of the day, we want to give it some credit for the dangerous area. We don't want to kill the flight test crew. So, what we learned so far, and I will wrap up very quickly. Technology-wise, we have a lot of experience in certain areas of the world where they developed control laws. We can use this experience. Success from failure is very close, and this is something that people have to really appreciate, is that you might be flight testing an aircraft for hours and hours and hours and never get into a proper optimal design. And yet one day you will wake up, have a bright idea, you do the job, and then everything works magically. It's not something which is entirely predictable. But the designers know this stuff anyway. So development is still risky. Risk may increase due to the objectively unknown areas. If you have your aerodynamics completely out of the loop with the basic aircraft that you are flight testing, sooner or later, you're going to have surprises. So, and by the way, everything that I've been talking about is not applicable only to helicopters. We will have also, in the long term, remote piloted vehicles or general aviation aircraft also will benefit from this technology. Now, for the certification part, it's nothing unusual. It requires knowledge. This is not secret from our side. But realistically and honestly speaking, following a project is really difficult. We need to be involved in all the changes, like step by step, and you have a good traceability of what has happened. And in other words, we need to have a continuous involvement, a very good cooperation, whether it's a certification authority, validation authority, and so on. It's difficult otherwise to get in the loop and avoid essentially to interfere all the time within the schedule of a company. So, and it's absolutely important that there is a mutual trust developed between all the authorities. And honestly speaking, Transport Canada and FAA have been really excellent in this department. We have nothing, absolutely not the nearest glitch. So something very important for the organization, and this is something sometimes is being overlooked, is like all what I'm talking about, whether it's a development within the house or certification, has to be done within a very demanding civil market. It's not the military. It's not the 5 or 10-year project that you can afford to develop and with endless amount of money. You need to do it. You need to do it in time and deliver the aircraft. And that exactly is what will sooner or later create some conflict with what I've already described. But this is normal business for everyone. So, as I said, I'm not going to keep you long on the subject. Half an hour. I hope it was enough and you have enough food for thought. And I'm sure everybody is going to be glad to answer some questions on this topic. Thank you. What do you do with this?
Thank you, Alexandros. You can take a seat next to your colleagues and we'll take questions from the room.
Eric Ferreira, Airbus Helicopters. A question to Mr. Germain related to the SAE group. You mentioned the hot topics of needed collaboration with STC, TC holder and engines, TC holder, related to the distortions of engines integrated on the airframes. How is your intention to proceed on an SAE level to cover this? Or maybe I rephrase my questions. Of course, there is a need to do a lot of demonstration of temperature and pressure distortion at engine inlet integrated on the aircraft, and this is most of the time an IP of the TC holder of this aircraft. Thank you.
Yeah, I think you answered your own question. It will be done. It's a case-by-case basis. But the biggest challenge, I think, for the STC applicants is not to demonstrate compliance more than knowing what to demonstrate. So the biggest problems we've seen is that the STC applicants don't have access to the engine installation manuals. Those limits are, secretly guarded, usually by engine OEMs and airframe OEM by intellectual properties laws, usually. So it is one of the hot topics. How to demonstrate after, then that's another story. We are working on finding means to minimize the cost. That's one of the goals of the committee as well. Without compromising safety. So it's a big challenge. We're still in discussion, obviously. That's one of the hot topics.
So we can take the next question from Slido. It's on inlet barrier filters. First one is the most important contributor to filter clogging is icing, which is out of scope of the IRP. How is icing handled together with filters?
Yeah, I can take the icing question. In my experience, generally, known icing isn't considered for filters, so those will be restricted. Louis David, you mentioned there was a AC.
Yeah, the SAE committee, SA4C, deals with that. We will only deal with the power available and distortion aspect of it. But yes, we do deal with icing for sure.
Thank you. So back to fly-by-wire. How will control loss changes be treated, minor, major, and who will make this assessment?
There is no, I don't believe there's anyone in this room that believes that control law changes should be treated as a minor, especially when we're talking about the control laws themselves. We're not talking about an outer loop gain or far away. You have like thousands and thousands of gains in every control law, and especially depending on each of the loops that you're building, the sensitivity of the control laws can be great. So it will be a case-by-case assessment. It will be an argumentation, and as usual, the companies are expected to make their own classifications internally, and later on that to have an agreement with us as well.
Next question, still related to fly-by-wire. Will the aircraft level FHA cover traditional functions? And if not, how will EASA ensure that these fly-by-wire FHA are harmonized with the FAA?
I am not so sure why we're building flight control laws if we can't analyze the FHA properly at the aircraft level. It has to take into account the fly-by-wire. There's no doubt about it. So the FHA, on the other hand, for many aircraft types is almost identical. If you take a Part 29, take a big let's say, like 20,000 pound aircraft being built in Europe and a 15,000 pound aircraft built in the United States, there's no difference on the functional hazard assessment. There is no question what's going to happen when I lose control. We're talking about functional. We're not talking about system safety assessment. Sometimes people do confuse a failure of systems as a prerequisite of a functional hazard assessment.
Thank you. We have a question in the room.
Well, it's a bit of a silly question, but a fly-by-wire, do you consider the robustness against electromagnetic pulses for nuclear explosions? You considered its robustness against those?
I am not so sure that I'm an electrical expert to answer to you on nuclear explosions, but I'm not so sure that any other aircraft, to be honest, is really capable of sustaining that so easy.
Well, mechanical linkages generally don't fuse, but
well,
electronics. If you're just fly-by-wire, is it going to cease flying when there's a little pulse?
I think I can guarantee you that if you're close to if you sustain an MC pulse of that sort of magnitude, there will be a lot more that is going to go off, not just your flight control system. So I think the military has a lot more experience on that. I'm afraid I can't answer to you on this one directly. I can see the next ones are also, wow. I think I'm going to keep you busy until lunch, unless you want to start leaving. The flight control system shall continue to operate. How to realize after fly-by-wire malfunction? Are you considering malfunction only as a hardware failure or software failure, as a unit failure? A fly-by-wire system has thousands of components inside, each of which can fail. So yes, it shall continue to operate. It must have certain probabilities, certain protections, but by no means we are talking about total fly-by-wire loss or malfunction. We're not talking about total, we're talking about partial. If you lose the fly-by-wire, you lose the aircraft, full stop.
Next question is back on the inlet filter.
It looks like it's a question for EASA. So based on the SAE outcome, do you foresee to revisit already installed IBF installation? So I don't know if anybody from EASA wants to answer. I can only speak under the SAE umbrella here.
Do we have an EASA expert on this?
That's a good question. We don't know.
We don't know. The same question could be asked to Mr. Kelly. I don't know if you can pass a microphone. And I expect EASA, Transport Canada, and FAA having the same thinking or similar thinking.
Yes, so the reason, one of the reasons for the beginning of the SAE S12 committee was because we were concerned about some of the installations that were out there that they may not have demonstrated compliance in terms of establishing power available, considering a dirty or clogged filter. So that's where it started. There have been some service difficulties, a few, with IBFs, but we're not aware of any in the areas specifically we've charged to the S12, which is power available and inlet distortion. We haven't had problems in those areas. So we know of no unsafe condition with IBFs that are out there in terms of power available and inlet distortion. So unless we see reason to do that, we would not go back and revisit those installations that are already approved.
Thank you. Last two questions. Fly-by-wire is the
I said
Bell
that
525.
keeps you busy till lunch. So fly-by-wire, is the Bell 525 and fly-by-wire in general meant to be covered by SCCS 29? Are there plans to expand SCCS 29 or to create a new specification? Clearly, the rules are not bad, they're very useful. However, for specific fly-by-wire topics, we do produce special conditions, at least on the EASA side. FAA, believe, are amending the rules accordingly, and on how the FAA would manage this precisely, I would rather let it to the FAA to answer. From our side, it's clearly a special condition amendment later necessary. Now, it will be published, it will be debated, and most of all, later on, when the time is considered appropriate, it might be incorporated into the basic CSs. But at the moment, when you do something first time on a rotorcraft, you have to see how it's going to work.
Thank you. We have a question on the back.
Good afternoon. David Evans from Babcock Mission Critical Services. I have a question for Alex regarding, you alluded to the functional hazard assessment and lessons learnt from fixed wing. If we look at loss of aircraft incidents such as Turkish Airlines and highly integrated systems from with the increased complexity of rotorcraft flight control laws, how can you ensure that in a functional hazard assessment you are going to identify all the failure conditions, whereas in the fixed wing we've seen where these have been missed and probably had a contributory factor to these accidents?
There is never a perfect world. Airbus has proven that when they originally introduced their fly-by-wire, exactly the same questions we had, if you remember. Now, it seems that since 1990s, when they introduced the first flight control laws and fly-by-wire, it seems that they've done something right, because we're still flying with them. And the accident rate is not as high as we would like to have. But, of course, you're right. There is extra vigilance here that is required, because yes, we're still doing something new. Yes, there is always the factor unknown. And yes, we try to keep margins, both the authorities as well as the manufacturers, about what can happen and what may happen that we don't know. I see there's a last one.
We have a last one on the left. No?
Is it possible and feasible to use a flying testbed helicopter to get credits? I've got to confess it's a little bit generic question, but I will try to make it a little bit more precise for you. If you demonstrate a helicopter is very close to what exactly you would like to certify, and if you demonstrate that precisely what credits you want to give credit to, I'm not so sure that you can't do it. But it's all in a case-by-case basis. I don't know anybody from the manufacturers that woke up one day and said, okay, now I'm going to design a new control law, I'm going to certify it. They tried it and tested it before they accumulated the experience they need and the confidence they need to put real aircraft and real people on them.
One last comment here on a question that appeared just a few minutes ago regarding the possibility of AC material for fly-by-wire. We, as the EASA does, we deal with fly-by-wire primarily by special conditions, as well as existing regulations. So we do have an advanced flight control handbook that is useful. That's out there to be used. I might also mention that recently the certification management team, the oversight, the executives, if you will, of the ANAC and TCCA and EASA and FAA approved an advanced flight control working group. That advanced flight control working group is going to be looking at the guidance that is authorities only for now, looking at developing recommendations that may result in guidance. So eventually it may find its way into the AC material, but for now they're being addressed mostly by special condition.
Thanks a lot.
Is there any additional question in the room? Yes, one on the back, Monsieur Lantéry.
I have a question for Alex. So thank you for your presentation. I think that the problem of the control law, the challenge of the control law is not the robustness of the control, the fly-by-wire itself, but do you think that the introduction of fly-by-wire will introduce a new concept of the cockpit? And do you think that we have all the tools to assess the future cockpit? And the challenge, I think the challenge will be to simplify the cockpit, to remove the automatic pilot control panel, for example. And do you think that we have all the tools to assess the future cockpit, which will be very simplified?
Well, Patrick, thanks a lot. I'm sure you're worried about it because the next you see the next cockpit is not going to be very complex. Let me get it straight. If I understood your question, yes, we do expect certain changes to happen in the cockpit. In a long term, some of the instruments might be used or might not be used. There is a lot of automation that is taking place. Nevertheless, the human factor remains absolutely crucial in this one because, make no mistake about it, we trust systems. They've saved a lot of lives so far, but they need to be monitored. And I'm not playing the conservative guy here. I grew up with fly-by-wire technology, and it's totally different when you fly yourself and out in the air and you monitor a system and you have a few seconds to decide what is the thing doing rather than sitting in a box and like an office with a desk with a computer and thinking, oh, yeah, it will do this or it will do that. So no, by no means we expect very quickly to remove the human factor or pilots from the cockpit.
Yeah, I propose now to close the session for this morning. Thank you very much to all the presenters we had on stage today. Now it's lunch break, and we have to go back at 1:45 in this room if you want to follow on Airworthiness, and Ops will be in the other room. It's a plenary session. Everybody has to come back in this room.